All right, how's everyone feeling today? Great. So we've been talking about electromagnetic induction, how if you physically move a wire in a magnetic field, the magnetic force that acts on the charges in the wire actually makes the charges start flowing. Thus, you get a new current called the induced current in the wire. So, for example, here, if I physically move this wire downward like this, all those little charges in the wire, they're going to go along for the ride. So this charge right here is going to be moved downward too. And this one's going to be moved downward. And this one's going to be moved downward. And that one's going to be moved downward. All these charges are going to be moved downward. And we know that moving charges in a magnetic field experience a magnetic force. So using the third right-hand rule for magnetic force, I keep my right hand open with my fingers and my thumb at a right angle, and I put my fingers in the direction of the red field lines, and then I keep my fingers in the red field line direction, but I turn my thumb to the way the wire is being physically moved, because that's the way all the charges are going to be moved. And since all the charges are going along for the ride and going down, they're going to experience a force out of the page or right along the axis of the wire. So if I was going to draw my hand, it would look like this. My right hand, here's my thumb. Here are my fingernails. No, that's not my fingernails. We wouldn't see the fingernails. So this here would be like my palm, and my fingers here go with these red field lines right here. And then my thumb goes with the way the wire is physically moved. And then the force magically comes out of the palm of my hand. So all of these little suckers are going to experience a force this way. And if they're all forced that way, you make that leap of understanding, well, then you're going to get a new current going that way. And that's called the induced current. And the light bulb would go off because the current goes all the way around the loop. So this part right here is acting like an EMF. Instead of using a battery that uses chemical reactions, we're using a generator by physically moving the wire, using that magnetic force. That's why sometimes, EMF is referred to as the electromotive force, because it's that force right there that's pushing the charges and making them go. Now, you can figure out the direction of the new current by using the fourth right-hand rule as well. The fourth right-hand rule says take your thumb and your pointer finger and your middle finger and put all three of them at right angles to each other, and then put your pointer finger in the direction of the red field lines. Turn your thumb to the way the wire is being physically moved, and then your middle finger shows the direction of the new induced current, and that would be out of the page. So the new induced current, whether you use the third right-hand rule or the fourth right-hand rule, would be out of the page. Notice this happens because this wire right here is going to be busting these flux lines. It's going to be busting through that flux line. And as long as the wire busts through the flux lines, you get an induced current. Now, interesting enough, if I took the wire and I moved it back and forth this way, I slithered it back and forth like my pen right here, then the wire wouldn't be busting through any flux lines. It only busts flux lines if it's physically moved up or down like this. Then the wire is going to be busting through those red field lines. Yesterday, we also talked about the fact that you don't have to move the wire. You can move the bar magnet as well. So if the wire is kept still, but the whole shebang bar magnets are moved up and down, if the bar magnets are moved up and down, once again, this wire right here is going to be slicing through these red field lines. And as long as the wire is slicing through the field lines, you're going to get an induced current due to the magnetic force. So you can either move the wire or you can move the bar magnets. Yeah.
What happens if the bar magnets rotate around the wire? Does it bust any flux?
It wouldn't bust any flux, no current produced. You know, if you rotate it around like this, that wire, no flux busted. So on that note of being able to move the bar magnets, let's look at this next case right here. Now we have that bar magnet, and the bar magnet has a magnetic field, and I'm going to kind of exaggerate it here and draw these field lines. And the field lines come out of the north and they loop around into the south. But nonetheless, if I physically move that bar magnet to the right, you could see that these field lines right here and right here, they're going to be busted by the wire right here and by the wire right here and by the wire right here and the wire right here. By busting those flux lines, we're going to get a new current in this coil. So there's going to be a current in these wires right here. And this light bulb will go off simply by pulling this bar magnet away. You're going to be asked to determine the direction of the current in that coil. Well, Lenz's law allows us to easily figure out the direction of the induced current. Bring up this diagram here. So we have to ask ourselves, hey, this new current right here, it's going to have its own magnetic field. What pole is going to be here that makes it difficult to move this bar magnet to the right? So the only thing we're going to be looking at, folks, is this pole right here. And the fact that we're pulling it away. And then you ask yourself, hey, that new current in the coil, it's going to have its own magnetic field. Which magnetic pole is going to be right here that's going to make it difficult for me to pull that south pole away from the coil? It's going to be a north. Because if this right here is a north, we know that opposite poles attract. And that would make it, so hard for me to pull the south pole away. So that's what Lenz's law says. Lenz's law says the new current is going to have a magnetic field that opposes the motion of the bar magnet. So if you're trying to pull away a south pole, this is going to be a north and this is going to be a south. And then as soon as you establish that, well, now we know the field lines come out of the north and they go around back into the south. And then we could use the second right-hand rule in reverse by figuring out the direction of the current. We used to line up our fingernails and put them in the direction of the baby currents. and then the thumb would point to the North Pole. But now we're doing the opposite. We're putting our thumb towards the North Pole, and then our little fingertips, our fingernails, tell us the direction of the currents in these loop-de-loops. So my hand here, like this, there's my thumb, and here's my fingers like this. And here's my fingernails. My thumb points to the North Pole, this one right here. And then my fingertips tell me the direction of the currents. So I know these currents are going to be going down. And if they go down, then right here, it's going to be going to the right. Now, sometimes the bar magnet is not going to be shown. And you're going to be told whether or not the magnetic field is increasing or decreasing. So here we're going on to new material now. More examples of Lenz's law. So let's say I have magnetic field lines going this way. And the bar magnets aren't shown. The bar magnets that produce that magnetic field aren't shown. And then you have a loop of wire. And the loop of wire is going to be like this tape. So it's going to be like perpendicular to the field lines. So this is what I'm going to be attempting to draw right here. Now, they're not going to show you the bar magnet. There are other ways of actually solving this, but the way I always solve it, I imagine the bar magnet that's there, and I imagine how the bar magnet would have to be moved. So see if you could follow me on this, people. So let's say that you're told that this magnetic field here is decreasing in strength. This is critical. This is critical. It's decreasing in strength. And then you're asked, hey, if this magnitude of magnetic field is decreasing, what's the direction of the induced current in the loop of wire? So the way I approach these problems is I think about the magnetic field around a bar magnet. And if you have a bar magnet like this, and I know it's a little bit more complicated, But just bear with me because this works. This will give you the right answer. We know that at the north end, the magnetic field lines are coming out of the north end. And of course, then they loop around, they go back to the south. But right outside the North Pole, they come out like this, yes? And then we know at the South Pole over here, the magnetic field lines go in. So even though the original problem didn't show us a bar magnet, I imagine one. I imagine a big bar magnet over here. And which pole would this be if the field lines are coming out of it? Which pole? Yeah, it's going to be more like this north right here. So this right here is going to be like the North Pole. And then way over there is going to be the South Pole, not shown. And then, since they say that the magnetic field is decreasing, guess what I imagine that bar magnet to be doing if this field right here is decreasing in strength? Well, it's only going to be decreasing if the bar magnet is doing what? Moving away. The bar magnet is going to be moving away. By moving away, when you move farther and farther and farther away from the bar magnet, the magnetic field gets weaker and weaker and weaker. So when it says decreasing, I imagine this end of the bar magnet here moving away. Now, this loop of wire, it's going to have its own field. It's going to have its own field. You know, it's a single loop of wire. You could think of it as a coil of wire. So you see that blue? You know, you could think about it like this, guys. This loop of wire is, you know, is kind of like the same as that loop of wire right there. So just like a coil of wire, it's going to have its own magnetic field because as soon as there's a current in this wire, new current in this wire, well, then there's going to be a new magnetic field around that current. And the question is, what pole is going to be over here? In other words, with this loop up here, what pole is going to be here, making it difficult to move this North Pole away? Because we know it's moving away because the field strength is decreasing. So it's going to be a South Pole. Because the South Pole would make it difficult to move that North Pole away. So this pole right here is going to be the South Pole of a bar magnet. Because that's going to make it hard to pull that north away. Opposite poles attract. Lenz's law says the new current is always going to have a magnetic field that opposes the motion of the bar magnet. So this is going to be a south, this is the north. So now I know I got all kinds of fields going on here, and field lines never cross or touch, but bear with me. This field here is going to be kind of going out around like this, going out around like this. Now we could use the second right-hand rule in reverse. Put your thumb in the direction of the north, and then your fingers tell you the direction of the new induced current. So the new induced current is going to be going down in front and then up and back. Or like right here, If this here is the south and this here is the north, then the new current is going to be going down in front and up and back. This is tricky business. A lot of physics going on here. I want to draw another problem, but it's even harder to see the bar magnet, especially like if you're watching this recording. But bear with me. Hopefully you'll be able to figure it out and see. So here, folks, we have a magnetic field that's into the page, like this. The bar magnets that produce this field are not shown. Then there's this loop of wire. That's parallel to the page surface. So these magnetic field lines are piercing right straight through it. And let's say we're told that this magnetic field is increasing. What you want to be able to figure out is the direction of the induced current. And of course, you're going to be using Lenz's law. So I have my bar magnet here, yes? With the north and the south pole. It's an imaginary bar magnet. If I have field lines going into the page, how am I going to imagine this bar magnet? And am I going to imagine it is like this right here? Or am I going to imagine it's like this right here? Which is going to be facing the screen? Yeah, the north is going to be closest, yes? The north is going to be closest because we know with a bar magnet, if this is the north, the field lines here come out of the north. So I could imagine my bar magnet here being the north, right there, yes? And then when they say that this field is increasing, that's very, very important. What am I going to imagine the bar magnet doing? Moving towards it. No. So if this north pole right now is moving towards it, a new current is going to be induced, and it's going to have a pole that's right out here, and then one behind the screen back there. So one right here, and then one, if I go behind there, back there. If I'm plunging in a north, what pole is going to be out front here? Another north. Why? Because that would make it difficult to push in the north, yes? So if this is the north and it's moving in because the field is increasing, there's going to be a north out here and a south around back behind. It's kind of hard to draw that there. But if there's a north out here, which way is the current? Clockwise or counterclockwise? Counterclockwise, because my thumb is going to point to that north pole out here. So my fingers are going to show the induced current going this way, counterclockwise. If you followed all that, bravo, bravo, bravo. Now, if you didn't follow all that, and you don't like using my imaginary bar magnet technique, you can figure this out other ways. Look, if this field is increasing, then guess what all these red X's are going to be doing? They're going to be getting closer together, yes? They're going to be getting closer together. And that's as if this line right here is gonna move in here, and that's gonna slice through. And you can figure it out using like the fourth right-hand rule and all. By getting closer together, it's the same thing as if this wire getting bigger. So if I put my fingers with the field lines and the wire going this way, notice my middle finger here tells me the direction of the new induced current. But I do Lenz's law with the imaginary bar magnet. All right, there's a follow-up assignment. It's a Nearpod assignment. You could do all of them, except there's one problem that has to do with two coils, and that's like the part of the setup for a transformer. And we'll be talking about transformers after tomorrow's test. So we'll pause here, and you could start that Nearpod, but I'll change the due date. It's not going to be due till after the test.